So let's define an infinite series, maybe something that looks like this, and this is just an example. Let's start at an index of 1, go to infinity of 5 to the n over n factorial, which would produce 5 over 1 factorial, 5 squared over 2 factorial, 5 to the third over 3 factorial, and so on and so forth. Let's call that a series of constants. Now, why is it a series of constants? Because every term is just going to produce a number. But there are also series that we could produce that have variables in them. Let's now make this change and start at an index of 1, go to infinity, and say x minus 5 to the n over n factorial. And now what's different is I've introduced a variable into this, which means every term will not just be a number, but have a variable. So when I plug in 1, I get x minus 5 to the first power over 1 factorial, x minus 5 to the second power over 2 factorial, x minus 5 to the third power over 3 factorial, and so on and so forth, all the way up to x minus 5 to the nth term over n factorial. And this is called a power series. And this particular power series would be centered at x equals 5. Why? Because every single one has a minus 5, minus 5, minus 5. Making connections to transformations, that means it's been shifted to the right 5. So every term contains a power of x minus 5. So let's say, for example, that x is a variable and that any infinite series that follows the form index of 0 to infinity, some number, x minus c to the n, which would result in a first term, a1 times x minus c to the first power, a2 times x minus c to the second power, a3 times x minus c to the third power, plus dot dot dot, a sub n, x minus c to the n, plus dot dot dot. Let's call this a power series centered at c, where c is a constant. Now there is an important caveat that I must make a distinction, okay? Every Taylor series is a power series. In last class, we learned about Taylor and Maclaurin series. So every Taylor series is a power series, but every power series is not a Taylor series. So the way that I would think about it is we have this kind of umbrella here. That's my umbrella of power series. And underneath this umbrella of power series, one of the special types of power series is my man Taylor. And Taylor is a power series. But all Taylor series are not power series. And let's say that Maclaurin series are like special Taylor series. So they kind of fall in that subset, if you will. So let's say that a power series can be viewed as a function because it has x's in it. And so the domain of this function would be a set of x's for which the power series converges. Now, why? Why would that domain be as such? Because guys, if a series is going to be approximating a function, I need to know what values of x can I use it for. So you're going to run into one of 3 cases. Very important. Option number 1 of your 3 possibilities is that your series converges only at c the center. Now, what would that look like? So here we have some function, and I have a polynomial that I've built for that function. Let's call this spot right here the center. And that polynomial only approximates that function at C and C only. Okay, so center only. Option number 2 is that the series, sorry guys, option number 2, there exists a real number, and we'll call that real number R, which is greater than 0, such that the series converges for absolute value x minus c is less than r, and diverges when x minus c is greater than r. Now, what in the heck is that saying? So basically, option 1 is saying center only. Option 2 is saying within a range of values. So what's left? Option 3, I didn't draw a picture of option 2, so let's draw a picture of option 2. So again, let's say we have some kind of crazy polynomial. And now that polynomial can be fit by that function, and that function can be fit but there is a certain range where it is a good fit and everywhere else it's not. Option 3 is that the series converges for all real numbers. And basically that's saying it is converges everywhere. Now this is the first time where we're really using this word converges to mean a good approximation for the function. What would that look like graphically? Again, we have our function, some sort of function, and basically our polynomial fits it everywhere. Now we're going to call R our radius of convergence. If the series converges only at the center, then our radius of convergence is 0. If our series converges everywhere, then our radius of convergence is infinite. And the set of all values of x for which the power series converges, we're going to call the interval of convergence. Now, I really think we need to have some sort of picture here about what I'm actually talking about. So I need to have a picture. We have this function, right? F of x. Now, ultimately, what is happening is this, okay? We're going to pick somewhere, some center value to build a polynomial. That polynomial could only be good, that's a really bad polynomial, for right there at the center. Now, this would be the case where it converges at the center only, meaning it's only a good approximation for my polynomial or for my function f of x only at the center. Now, if it converges at the center only, that means my radius is 0. And my interval of convergence is only at the center, C. Now, option 2 would mean, maybe there's a range of values where it's pretty good for. So, let's say that out this way it's pretty good fit, and out this way it's a pretty good fit, but after that, it kind of goes away from the function. And so essentially what we're saying now is there is a range of values that is a good fit for the function, and we would determine that the distance from here to here, we would call that the radius of convergence. And for the purposes of this example, let's call this A and let's call this B. And the interval of convergence would be from A to B. Okay? Now, it is also possible that maybe you have an approximation for this function that works everywhere. And if that's the case, then my radius of convergence is infinite, and my interval of convergence is all real numbers. So these are our three possible situations. So I want you to get an idea of what exactly we're doing. So we've used the ratio test to find whether a series converges or diverges. But the ratio test is also important because it's going to help us to find a radius and interval of convergence. Now, if you remember, pretty important, the ratio test says that a series will converge if the limit is less than 1. So that's really important. We want to make all series produce a ratio test of less than 1 because then it's going to converge. So what we're going to do is we're going to find the limit and we're going to determine the values of x for which the limit is less than 1. We're going to basically force the series to converge, and I want to know what values of x it's going to work for. Now, to really drive this point home and illustrate this, what I'm going to ask you to do is to go to your calculator, and I'd like for you to graph sine of x. I would also like for you to graph a Maclaurin polynomial for sine of x, but let's only go out to 3 terms. I just want you to go out to 3 terms. Stop there. Okay, so we built this last class. Now we know that sine of x looks like this. Okay, there's my interesting attempt at sine of x. And so we know that this value here is pi, and this value here is 2 pi. And we're going to go from 1 to -1. And here is negative pi and -2 pi. What's kind of interesting here is when you go graph the polynomial, you're going to notice that this polynomial is going to be pretty close to these values all the way until about right there. And on this side, it's pretty close. Oh, that's terrible. Here we go. Pretty close until it starts to get farther away. And we could suspect what would happen if I added more terms, then we would get a better approximation farther out. And so this range right here, where we're pretty close, would be called the interval of convergence. Okay? So I want to walk you through this process of how you're going to actually be finding the interval of convergence and the radius of convergence. And in this case, if we built this at 0, the radius would be from here to here. And this process is kind of tricky because it's gonna have a couple of little finer details, so you gotta pay attention to the details here. So we're gonna use the ratio test. If you hear one thing that I'm doing all class long, I want you to hear this. Every time you are asked to find the interval of convergence, you must check to see if the endpoints are included. So important. So I've got this crazy looking power series. And it's got x's in it, it's got n's, all this sorts of stuff. We're going to execute a ratio test. Now remember that in a ratio test, and I would tell you to write small, we're going to take the limit as n approaches infinity. Remember that our numerator is going to have all of our n plus 1th terms. So -1 to the n plus 1 plus 1, x minus 5 to the n plus 1, parentheses n plus 1 times 2 to the n plus 1. Our denominator is going to have the original, -1 to the n plus 1, x minus 5 to the n divided by n times 2 to the n. Now my caution is, please write it as a compound fraction first. Don't go ahead and skip to multiplying by the reciprocal. I would prefer that you go ahead and do that. Because this is an absolute value, these -1s aren't going to matter at all because we're going to end up making everything positive anyways. So go ahead and obliterate that. Get rid of it. And then let's multiply by the reciprocal. The limit as n approaches infinity, x minus 5 to the n plus 1, n plus 1 times 2 to the n plus 1. Multiplying by the reciprocal, we're going to have an n times 2 to the n in the numerator and an x minus 5 to the n in the denominator. Now I want you to go piece by piece here and deal with each of the things. Now this 2 to the n and 2 to the n plus 1, we can actually simplify that. We're linking our work with equal signs. Remember that when you have two things that have the same base and we subtract, or have the same base and they're divided, we subtract. So we're going to go n minus n plus 1, which is going to become n minus 1, or just -1. So what does that tell me? That tells me that I'm going to have a 2 to the power of -1 in the denominator. So I'm going to put, 2 to the power of 1 in the denominator because it's negative. Now, the n and the n plus 1, these cannot be simplified. So go ahead and just bring them, n in the numerator, n plus 1 in the denominator. Okay? We're also going to simplify these x minus 5s because they have the same base. So we're going to subtract. N plus 1 minus n is just going to be 1. So that means I'm going to have an x minus 5 in the numerator. So here's my simplified pieces. Now you need to know that this limit only depends on n. So if this limit only depends on n, why don't I take the things that don't have n's and put them on the outside? Now they're still going to need absolute value bars around them. And so basically what I'm doing is I'm taking that piece to the outside of the limit, since the only things I really need to keep inside of my limit are the n and the n plus 1, since those are the n's. So what I'm going to ask you to do is I want you to evaluate this limit. Keep your x minus 5 over 2 out in front. Now we know because of Eats DC, exponents are the same, divide coefficients, that really this is going to produce a limit value of 1. And so we look at this and we're like, well, what now? Now remember up above where it said we want to make a series converge. If I want to find the interval of convergence or the radius of convergence, I need to make it converge. How do I make it converge? I'm going to make it converge by setting it less than 1. You will always do this because the ratio test converges if it is less than 1. Now what I'm going to do is I'm going to solve for x that makes this true. So what we essentially get is if I want this series to converge, I have the absolute value of x minus 5 over 2 is less than 1. And we're going to find the values of x where that's true. Now, students always forget that in Algebra 2, you guys learned how to deal with absolute value inequalities. So let me remind you. If you have an absolute value inequality that is less than 1, that means it could be within a range of positive and -1, and you're going to drop the absolute value signs. It means you're 1 unit away. Now I'm going to multiply the 2 to both sides. So we'll multiply by 2, multiply by 2, multiply by 2. And what I get is -2 is less than x minus 5, which is less than 2. We're going to add 5 to both sides, all sides. And I get that 3 is less than x is less than 7. Now here's what this is telling me. When I think about this certain power series, I know it's centered at 5. How did I know that? Because of the x minus 5s. I know that it's going to converge everywhere up until 3 and 7. But unfortunately, you don't know if it converges at 3 and if it converges at 7. Which goes back to every time you're asked to find an interval of convergence, you must check to see if the endpoints are included. So, here we go. I'm going to clean this up just a little bit, make this a little bit smaller so that we have some room, and I hope you have room on your paper. Uh-oh, crash my notability. There we go. All right, so we're going to make this a little bit smaller, get some room here, and basically what we need to do now is we need to check endpoints. Now this is the part that students really hate. Okay, so we know 3 to 7, everything in here is good. We want to figure out what's going on between 3 and 7. So checking endpoints. How do I do that? So if we go back up and we look at our original series. Our original series was the sum from n equals 1 to infinity of -1 to the n plus 1 x minus 5 to the n over n times 2 to the n. And our endpoints are 3 and 7. So what we're going to do is we're going to plug in 3 and we're going to plug in 7 and we're going to see what happens, and we're going to use our series test. So start, and we're going to let x equal 7. If I plug in 7 into this series where there's that x right there, I'm going to get -1 to the n plus 1, 7 minus 5 to the n over n times 2 to the n. Well, I can simplify that. N equals 1 to infinity, -1 to the n plus 1. That becomes 2 to the n over n times 2 to the n. I can get rid of my 2 to the n's, and this series becomes -1 to the n plus 1 over n. And -1 to the n plus 1 is just going to be the sum of 1 over n. And we know, this is going to be an alternating series. Oh, sorry about that. We know that this is going to alternate. I was thinking about the other one. It's going to decrease in magnitude. If I take the limit as n approaches infinity of 1 over n, I get 0. This thing is going to converge by the alternating series test. Now, what does that tell me? That tells me that 7 is going to be included in my endpoints, so I'm going to put an or equal to underneath the 7. We're going to do the exact same thing, but now we're going to let x equal 3. This one's a little bit spicier. Remember that we're plugging into this function. So we're going to get the sum from n equals 1 to infinity, -1 to n plus 1 power, 3 minus 5 to the n over n times 2 to the n. Let's simplify it. The sum from n equals 1 to infinity, negative 1 to the n plus 1, negative 2 to the n times 2 to the n. My recommendation is to pull the negative 1 out of this thing. So I get the sum from n equals 1 to infinity, negative 1 to the n plus 1. Write this as negative 1 to the n times 2 to the n over n times 2 to the n. Now, how did I know that? Because if we think about this as negative 1 times 2 to the n, then I can split it apart into these two pieces. Now, what I want you to do is to now combine these. If I combine those, I get n equals 1 to infinity, negative 1, n plus n is 2n plus 1, 2 to the n over n times 2 to the n. Just like we did before, get rid of your 2 to the n's. And so now, what is going on with this negative 1 to the 2n plus 1? Guys, that's always negative. If you plug in terms, no matter what, it's going to be odd powers. Odd powers. So essentially, this series is now the negative harmonic series. It's just a negative harmonic series, which we know diverges by p series. So what does that mean? 3 is not included in our endpoints, so it's going to keep its less than sign. So what is your final answer? Because we just did a butt ton of work. What is our final answer? I don't have a ton of room, so I'm going right here. Here's our final answer. We know that our interval of convergence is from 3 less than x less than or equal to 7. We could also write that as parentheses 3 comma 7 with a bracket. Our radius of convergence, because remember this thing is centered at 5, is going to be 2 units. So the radius is equal to 2. Remember that your center is 5. So all of this work to basically find out, I can use this as an approximation only if I'm within 3 and 7, not including 3. Okay? It is important to know that if you ever see something like this, that is also denoting an interval. An opposite facing bracket means the same thing as an open non-inclusive parentheses. Now the AP exam is not going to use that, but you could see that in a college level calculus class, so I just throw that in there. So if you had the interval parentheses a comma b with a bracket, you might see that written in this way right here. Similarly, I could say that these two things are the same or that these two things are the same. Like I said, you won't see this on the AP exam, but some college professors might use that notation. So I want to do another one with you. Don't worry, this one's not as long. In fact, these are the other two cases. As you can probably guess, I'm going to go through all 3 of the cases. So that was the one where we were case 2 and the series converged within an interval. So what will the other 2 look like? You will always start with a ratio test. So we're going to go add a power, negative 1, n plus 1, x to the 2 parentheses n plus 1 over 2 parentheses n plus 1 factorial divided by negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Honestly, that's the worst part. Because this is an absolute value, I don't really care about those alternating pieces at all. I would also hope that you could look at this and know that this is centered at 0. How do I know that it's centered at 0? Because it's not x minus something. It's just x. So it's centered at 0. Use your knowledge of transformations to make that assumption. We're going to go ahead and simplify this. This is going to be 2n plus 2 plus 1. So that will become x to the 2n plus 3. In the denominator, again, we could do that same thing. 2n plus 2 plus 1 is going to give me 2n plus 3 in parentheses factorial. Multiplying by the reciprocal, we have 2n plus 1 factorial and x to the 2n plus 1, close brackets. Now I want you to do a little bit of work with your factorials, because remember, this one would start at 2n plus 1, then go to 2n, 2n minus 1, 2n minus 2, so on and so forth. In the denominator here, this one would start with 2n plus 3, 2n plus 2, 2n plus 1, 2n, 2n minus 1, dot, dot, dot. So what would eventually happen is the 2n plus 1s would go away, the 2n's would go away, the 2n minus 1s, and everything from here on, leaving you just those two things in the denominator. So my factorials basically are going to simplify down to just give you a 2n plus 3 and a 2n plus 2 in the denominator. Well, what about our powers of x? Here I have x to the 2n plus 3, and here I have x to the 2n plus 1. Let's subtract 2n plus 3 minus 2n plus 1. Doing a little bit of distributive property, I get 2n plus 3 minus 2n minus 1. 2n's go away, and 3 minus 1 is 2. So that means it's just x squared. So what do we do with this? Because the only thing that this depends on is n, we're going to leave these in, and then I'm going to take this x squared, and I'm going to put it on the outside of my limit. So we're going to move it to the outside. And I basically get 1, 2n plus 3, 2n plus 2. You should still have absolute value brackets. Now we're going to evaluate this limit, and because it is bigger on bottom, I know that this limit is going to produce 0. Now, anything times 0, remember our goal is to find the values of x for which this thing converge. And this thing is going to converge anytime it is less than 1. We want to make it converge. That is the goal. We want to force this series to converge by making whatever values of x it has less than 1. But guys, anything times 0 is 0. And 0 is less than 1 always. And x goes away. Why? X goes away because I'm multiplying by 0. And if I'm multiplying by 0, I get 0 is less than 1, which is a true statement, always. Now this is going to confuse you because you're like, okay, that means it converges nowhere. Wrong. This actually means this converges everywhere, because that means it doesn't matter whether I get any value of x. It's going to converge for all x because this is always true, no matter the value of x. So that tells me that my radius is infinity and my interval of convergence is negative infinity to infinity. So big takeaway, if the limit yields 0, then the series converges everywhere for all real numbers because it doesn't matter what x is. In the previous example, it did matter what x was because I didn't make x go away. X wasn't gone. My limit didn't produce 0. So we've got one of the other cases. Let's do the last one. Same concept. We're going to use the ratio test. We're going to add a power, x minus 3 to the n plus 1 power. Luckily, this one doesn't give us a gross, nasty compound fraction, which is good. Let's simplify these factorials. N plus 1, n minus 1, so on and so forth. This is going to be n minus 1, n minus 2, so on and so forth. And so basically, those are going to go away, and it's just going to leave you with an n plus 1 in the top. Okay, we want to also simplify our x minus 3s if I take n plus 1 and I subtract n, you're just left with 1. So that tells me that I'm going to have an x minus 3 to a power of 1. Well, my denominator completely went away. Okay, well, what next? Because this x minus 3 doesn't depend on anything, let's move it to the front of our limit. So we're going to have absolute value of x minus 3 here. We're going to have a limit as n approaches infinity of n plus 1. Now I want you to actually take that limit. This limit is going to be infinitely big. And remember that our goal is to figure out when this is going to be less than 1. But how am I going to make something that is infinitely big less than 1? That's never true. So if I can't make something that is infinitely big, no matter what I multiply it by, less than 1, then this thing is never going to converge anywhere else but the center. That means if this thing is centered at 3, which I can see, it's going to converge at 3, but nowhere else. Well, why will it converge at 3? Because I built the polynomial at 3. So it's going to converge at the center of 3 only. Okay? That means that my interval of convergence is just the value 3. My radius of convergence is just 0. Something important happens from all this. We notice that these types of polynomials and series are always going to converge at their center. Why? Because if I plug in x equals c, what's left is a finite number, just 0. And that means that in this expansion, all of the terms after the first term are going to collapse at the center. Okay? I would tell you, I do think it's important that you have all of your factorials memorized. So you may want to kind of throw those up in your memory. I think through 5 is pretty easy, but once you get into 6 and 7, I would go ahead and lock those up in your memory. So last and final thoughts here before we close. I think it's important for you to know that when you're doing an interval of convergence problem, if the limit as n approaches infinity gives you something times infinity, then that's infinity, and it's never going to be less than 1, which means it's going to converge at the center only. If your limit as n approaches infinity gives you something times 0, 0 is always less than 1, this is going to converge everywhere. If your limit as n approaches infinity gives you something times a number, then you're going to have to test endpoints, and it's going to converge on an interval. Probably pretty important that you write that down. Okay? That's where I'll stop.